In the centre of the Milky Way, where light itself vanishes into darkness, an invisible force holds dominion over everything. It is 4 million times heavier than our Sun, yet it hides behind a curtain of dust and silence. This immense gravity well sits at the core of our galaxy, orchestrating the movement of 400 billion stars with the precision of a cosmic clock. Every world, every cluster, every drifting cloud of gas within our spiral arms dances to its pull. The stars that seem to twinkle aimlessly above us are not random wanderers. They move in a vast choreography so exact that even chaos itself becomes an illusion. Our entire solar system is one of the dancers, racing through the galaxy at over 500,000 miles per hour, tracing an orbit so large that it takes more than 200 million years to complete. The last time we passed through this region of space, dinosaurs still ruled Earth, and through all those eons something unseen has been guiding our path. For centuries, astronomers believed the answer was simple: gravity from all the stars, acting together, holding the Milky Way in balance. Like dancers gripping one another's hands in a spinning circle, each star was thought to tug on the next, creating harmony from chaos. The numbers seemed to agree. But when scientists began to measure the actual speeds of stars near the galaxy's edge, the truth began to fracture. Those outer stars were moving far too quickly. By Newton's laws, they should have been flung out into intergalactic space long ago. Yet they remained, trapped in orbit by a gravity too strong to be explained by visible matter alone. Somewhere deep in the galactic heart, an unseen anchor exerted a pull greater than any known cluster or nebula. Something vast and compact lurked there, invisible but undeniable. Imagine a table covered in iron filings, each one aligning to the pattern of a magnet you cannot see. From above, the filings trace spirals and loops that reveal the magnet's hidden presence. Our galaxy behaves the same way. The motions of billions of suns reveal an invisible hand at the centre, an object so powerful that its gravity sculpts the Milky Way's shape itself. Astronomers turn their telescopes toward the heart of the constellation Sagittarius, the direction where this unseen force must reside. But visible light revealed nothing. Dense clouds of interstellar dust blocked the view, hiding whatever lay beyond. For decades, the centre of our galaxy remained a mystery, cloaked in darkness, betrayed only by the motion of the stars around it. It was like hearing an orchestra play while the conductor remained invisible. The melody made sense only if someone was there to guide it. Then, in the 1970s, technology gave humanity a new kind of vision. Radio telescopes capable of seeing through the dust that blinded optical instruments began probing the galactic centre. What they found was astonishing: a single point of energy brighter than anything else in the Milky Way at radio wavelengths. It wasn't a star, nor a nebula, nor any known cosmic object. It was a compact source radiating with immense power, yet invisible to every other form of light. Astronomers named it Sagittarius A star, marking it with an asterisk as if to warn, here lies something extraordinary. This discovery changed everything. For the first time we had found the signature of the unseen master at our galaxy's heart. But what exactly was it? A star cannot shine so fiercely in radio waves without being visible in light. A gas cloud cannot remain so compact without collapsing or dispersing. The source seemed impossibly small, yet it released energy beyond imagination. It was as if the universe itself were whispering that something far beyond ordinary physics was hiding there. The invisible gravity that held the galaxy together now had a name, but not yet an identity. Over the next decades, scientists would pursue that mystery relentlessly. They would measure the orbits of stars so close to this hidden object that their paths curved like whips in space. They would track invisible radiation that pulsed with the rhythm of something spinning faster than comprehension. They would use every wavelength, infrared, radio, X-ray to peel back the layers of dust and shadow that shielded the galactic core. And with each discovery, the truth would grow clearer and stranger. Something beyond all human experience resided there, a place where time slows, where gravity traps even light, where the fabric of space itself folds inward upon nothingness. The Milky Way, for all its beauty and complexity, revolves around this silent abyss. Our planet, our sun, our very existence, each depends on the pull of a monster that does not emit a single photon of light. In the vast dark, the galaxy's heart beats in gravity alone. That is the power of Sagittarius A star, the hidden giant whose presence we sense only through the way it bends the universe around it. The mystery began not with what astronomers could see, but with what they couldn't explain. For centuries the night sky had appeared predictable, obedient to the laws of gravity first described by Newton. Yet as telescopes became more precise, those same laws seemed to falter at the edges of the Milky Way. The outer stars were moving too fast, whipping around the galactic disk as if pulled by an invisible rope. According to the mathematics of gravity, they should have flown off long ago, scattered into the emptiness beyond. But they hadn't. Something unseen was holding them in place. The equations no longer balanced, and that imbalance haunted every scientist who studied the cosmos. The Milky Way was a majestic spiral, yes, but it was also a puzzle that refused to yield its final piece. When astronomers plotted the orbital speeds of stars at various distances from the centre, they expected to see a gradual decline. The farther from the middle, the weaker the gravitational pull should be, just as planets far from the Sun move more slowly. Yet the data refused to cooperate. The graph flattened out, the stars circling at nearly constant speed no matter how distant they were. That was impossible unless there was far more mass in the galaxy than the stars and gas we could observe. Either our understanding of gravity was flawed, or most of the universe was made of something invisible. This realization marked the birth of one of science's greatest enigmas, dark matter. Some speculated that the missing mass might consist of faint dead stars or giant gas clouds too dim to detect. Others proposed more radical ideas. Perhaps space itself contained unknown particles that exerted gravity but emitted no light. Whatever the answer, it meant that the Milky Way, and every galaxy like it, was shaped by forces hidden from human eyes. But even dark matter couldn't explain the violent motion seen near the galactic centre. There, stars moved in tight, furious orbits, their velocities reaching thousands of kilometres per second. They weren't just orbiting an invisible mass, they were orbiting something concentrated, compact, and unimaginably dense. It was as though the entire weight of millions of suns had been crushed into a space smaller than our solar system. No ordinary object, not even a cluster of dead stars, could account for that. The evidence hinted at something stranger, something that defied the limits of physics as then understood. The word singularity began to creep into scientific conversations, whispered with both excitement and unease. A singularity, a point where matter collapses infinitely, where gravity becomes so intense that space and time themselves bend into a closed knot. The idea had emerged from Einstein's theory of general relativity, but many dismissed it as a mathematical curiosity, not a real object that could exist in nature. Now the motions of the galactic core suggested otherwise. Observations pointed to a region of space radiating vast energy, yet too small to be any kind of conventional source. As technology advanced, astronomers mapped that region across multiple wavelengths. In visible light it remained pitch black, but in radio frequencies it blazed with activity. Something was hiding behind the dust something that devoured matter and spat out radiation. Sagittarius A star became the prime suspect. But the riddle deepened. If this was truly a black hole, how could it radiate anything at all? A black hole, by definition, allows no light to escape. Yet the signals persisted, strong and steady. Scientists realized they weren't seeing the black hole itself, but the furious environment surrounding it, a maelstrom of superheated gas spiraling inward, glowing fiercely as it approached the point of no return. Every photon emitted from that dance of destruction carried information about the monster at the centre. Piece by piece, a portrait began to form. Still, skepticism remained. Astronomers are cautious by nature, and extraordinary claims demand extraordinary proof. They considered every alternative. Could the central object be a cluster of neutron stars packed tightly together? Could it be a swarm of dark remnants orbiting one another? Each theory failed under scrutiny. Any such cluster would tear itself apart within a few thousand years. Only one explanation fit all the data. A single, massive, compact object exerting a gravitational field so extreme that nothing, no light, no matter, no information could escape its grasp. The concept was both terrifying and beautiful. The Milky Way was no gentle spiral of stars drifting in cosmic peace. It was a dynamic, turbulent system bound by an abyss at its heart. The galaxy's grace came from violence, its symmetry born from collapse. Every sunrise on Earth, every calm night sky, owed its stability to a black hole we could not see. And yet, that understanding was still incomplete. Knowing that something invisible existed was not enough. Humanity wanted to see it, to capture its image, to confront the dark face of gravity itself. The instruments of the 20th century had revealed the puzzle, but solving it would require a new kind of vision, one that could peer through dust, through light, even through time. The universe had given us a riddle, and at its centre lay not emptiness, but an enormous silent truth. For generations, the heart of our galaxy remained a hidden world, sealed behind a curtain of cosmic dust so thick that no ordinary telescope could pierce it. The Milky Way's centre lay in the direction of the constellation Sagittarius, a region glowing faintly with scattered starlight, but obscured by vast lanes of gas and interstellar debris. For centuries, astronomers stared into that darkness and saw nothing but mystery. It was a blind spot in our understanding of the universe, a place we knew existed but could not see. The tools of traditional astronomy were useless there, like eyes straining through fog to glimpse a lighthouse miles away. Yet even in that obscurity, something was happening. Stars were moving at impossible speeds, clouds of gas were heating to millions of degrees, and strange bursts of energy were escaping from the void. The clues were there, but they were hidden in a spectrum our eyes could not perceive. The breakthrough came when humanity learned to see the universe not just in light, but in wavelengths far beyond it. The rise of radio astronomy in the mid-20th century transformed the way we explored the cosmos. Suddenly, the sky that had once been dark became alive with invisible signals. Massive dishes began listening to the whispering static of the universe traces of radiation emitted by stars, pulsars, and galaxies billions of years old. When scientists pointed those instruments toward the galactic center, they discovered something extraordinary, a faint but steady signal coming from deep within Sagittarius. It was unlike anything seen before, a concentrated radio source, compact and powerful, smaller than any known nebula, yet brighter than any single star in the Milky Way at that frequency. This strange beacon did not vary with time, nor did it move across the sky. It sat fixed at the exact center of our galaxy, as though marking the spot where the invisible force we had long suspected truly resided. In 1974, astronomers Bruce Ballack and Robert Brown made a decisive observation that would change everything. Using radio telescopes in Greenbank, West Virginia, they measured the emissions from this mysterious point and confirmed its compactness. The source was barely a few light-hours across, yet it radiated the energy of 1 million suns. They named it Sagittarius A Sagittarius A, designation that hinted at its singular importance. The asterisk was not just a symbol, it was a warning. Whatever lay there was no ordinary star. Over time, radio observatories around the world joined the hunt. Interferometry techniques allowed multiple telescopes to act as one enormous eye, linking signals across continents to sharpen the image. What emerged was both thrilling and perplexing. Sagittarius A was incredibly small, extraordinarily energetic, and eerily silent in visible light. It emitted no optical glow, no flicker, no sign of the heat one might expect from a star. Instead, it hummed in radio frequencies with the precision of a cosmic heartbeat, a steady rhythm that pulsed through the galactic center. Each discovery deepened the mystery. Astronomers ruled out every ordinary explanation. It couldn't be a cluster of stars, they would have scattered. It couldn't be a neutron star, it was too massive. It wasn't a quasar or an active galactic nucleus either. Those belonged to distant galaxies, not our own. What remained seemed impossible. A massive object invisible to all but radio waves. And so scientists began to suspect that they had stumbled upon a black hole. The idea felt like stepping into science fiction, yet the evidence grew harder to deny. Theoretical models predicted that as matter spiraled into such an object, it would heat up, releasing radiation before disappearing forever beyond the event horizon. That matched exactly what the radio telescopes were detecting, an inferno of energy at the threshold of invisibility. But even so, the concept was difficult to accept without direct proof. The scientific mind demands evidence that can be measured, repeated, verified. Radio astronomy had revealed the presence of something monstrous, but no one had yet seen its gravitational fingerprints with clarity. It would take decades of relentless observation and technological evolution before that shadow could be traced. Still, Sagittarius A became a point of fascination, a cosmic enigma that inspired new generations of researchers. To peer into the dust was to look into the unknown, to search for a creature that swallowed light yet shaped the heavens. It reminded humanity that the universe was not just a collection of stars, but a dynamic, living system filled with forces far beyond our comprehension. Every radio wave captured by those enormous dishes carried a fragment of a secret billions of years old, a message from the heart of the galaxy. With each observation, astronomers were not just listening to noise, they were listening to the Milky Way breathe. The dust had hidden the truth for eons, but now, with new eyes tuned to invisible light, we were finally beginning to hear the song of the darkness itself. At the heart of the Milky Way, behind the veil of dust and the roar of radio waves, lies an engine of staggering power. It cannot be seen, it cannot be touched, and yet its influence extends across 50,000 light-years, holding every star in its gravitational embrace. Sagittarius A star, once only a mysterious signal on radio charts, had become the centre of the greatest cosmic riddle of all. What mechanism could produce so much energy from such a small region of space? The numbers refused to make sense. The object was no larger than the orbit of Mercury, yet it released bursts of radiation with the strength of entire stellar clusters. Something inside that darkness was converting matter into energy with impossible efficiency. The laws of physics demanded an explanation. In the late 20th century, astronomers began to understand that what they were observing was not the source itself, but the chaos surrounding it. Matter drawn toward Sagittarius A star didn't simply fall straight in. It spiraled, forming an accretion disk, a swirling maelstrom of gas and dust heated to millions of degrees as it raced ever closer to oblivion. Friction and magnetic turbulence tore particles apart, releasing radiation across the spectrum. It was this glowing inferno that radio telescopes had captured, not the black hole itself. The black hole remained hidden, its boundary defined by the event horizon, the invisible line beyond which nothing, not even light, could return. This realization transformed the mystery into a revelation. For the first time, humanity understood that the Milky Way's central power was not a cluster of stars or a conventional source of light, but a supermassive black hole, millions of times heavier than the Sun. It was the ultimate engine of destruction, yet paradoxically, it was also the architect of creation, shaping the galaxy's structure through its gravitational influence. Every spiral arm, every orbiting system, every drifting cloud of interstellar gas existed in balance because of this singular point of gravity. To the human mind, it was almost poetic, a silent void giving order to billions of suns. As astronomers studied Sagittarius A star more closely, they realized that black holes are not simple vacuums devouring everything around them. They are dynamic systems that interact with their environments in complex and sometimes elegant ways. When matter falls inward, magnetic fields twist and snap, generating immense jets of energy that shoot from the poles at nearly the speed of light. In distant galaxies, such jets can extend for thousands of light-years, illuminating space with streams of radiation. Sagittarius A star, however, is unusually quiet. It slumbers most of the time, feeding only on small amounts of interstellar debris. Yet even in its stillness, it holds unimaginable power. Occasionally it flickers, brief surges of X-rays or infrared light betray the momentary fall of matter across the event horizon. These flares last mere minutes, then fade again into silence, like sparks from a sleeping dragon's breath. Scientists have long wondered why our galaxy's central black hole is so calm compared to others. Some suspect that most of its available fuel has already been consumed, leaving only thin traces of gas to fall inward. Others believe magnetic fields or stellar winds from nearby stars may keep fresh material at bay. Whatever the reason, Sagittarius A star is a sleeping giant stable now, but capable of awakening with catastrophic force if a large enough mass drifts into its reach. The more scientists observed, the clearer the picture became. Every piece of data, every orbit measured, every flash recorded pointed to the same conclusion. The unseen engine at the core of the Milky Way was not a metaphor or an abstract theory. It was a real, physical object obeying the laws of relativity with exact precision. Its gravity warped the space around it, curving the paths of nearby stars into elegant ellipses. The closer those stars orbited, the stronger the curvature became, until time itself began to distort. To approach the centre of Sagittarius A star would be to enter a realm where seconds and hours no longer agreed, where the familiar order of cause and effect began to unravel. The black hole was not merely a thing, it was a region of space-time behaving according to rules that defied intuition. And yet, despite its terrifying reputation, there was beauty in its perfection. A black hole is pure geometry, a seamless equation made real. It has no surface, no colour, no texture, only gravity, mass, and the curvature of the universe itself. In its simplicity lies its mystery. To study it is to confront the limits of human understanding, to stand on the edge of what physics can describe and glimpse the domain of the infinite. Sagittarius A star, the unseen engine, is both the destroyer and the keeper of cosmic order. It is the silent conductor of the galactic symphony, the invisible hand that holds the Milky Way together. And though we cannot see it, we feel its presence in every movement of the stars. By the end of the 20th century, the idea that a supermassive black hole lay at the centre of our galaxy had transformed from speculation into conviction, but conviction still demanded proof. To truly confirm the existence of Sagittarius A star, astronomers needed to witness its gravitational pull in action. They needed to see how it shaped the motion of nearby stars, how it dictated their paths, how it warped space itself. The problem was that the galactic core is not a place of clarity. It is buried behind curtains of dust and gas so thick that visible light cannot escape. Traditional telescopes could only record a murky haze. To look into that chaos required a new kind of vision infrared. Infrared light, with its longer wavelengths, can pass through the interstellar dust that blinds ordinary optics. In the 1990s, a new generation of astronomers began using infrared detectors to peer deeper into the galactic heart than ever before. Two rival teams, one led by Reinhard Genzel at the Max Planck Institute in Germany, and another by Andrea Ghez at UCLA, dedicated decades to mapping the orbits of stars around Sagittarius A star. They used some of the most advanced observatories on Earth, from Chile's Atacama Desert to Hawaii's Mauna Kea, combining adaptive optics and precise measurements to track stars that danced faster than anything previously observed. These stars were like glowing embers caught in a whirlpool of gravity. Their movements were wild yet orderly, chaotic yet mathematical. Over the years, astronomers plotted their positions again and again, building a time-lapse portrait of motion around an invisible point. It was like watching a cosmic ballet unfold in slow motion, with each performer tracing a perfect path defined by the hidden mass at the centre. What they found defied imagination. Some stars completed full orbits in mere decades, racing through space at speeds exceeding 16 million miles per hour. That meant whatever they were orbiting had to be immensely massive, far beyond the combined weight of all the visible stars in the region. The data left no room for alternatives. Only a black hole could compress millions of solar masses into such a tiny volume. The discovery was electrifying. For the first time in history, humanity could watch gravity in its most extreme form, not as a theory but as a spectacle. These dancing stars, as they came to be called, became the key witnesses to the black hole's existence. Each orbit was a signature, each curve a sentence in the story of space-time. One star in particular stood. It was bright, fast and bold, weaving a path so close to Sagittarius A star that it skimmed the edge of the event horizon's influence. Astronomers named it S2, and it would soon become the most studied star in the Milky Way. But even before S2 revealed its secrets, the collective dance of these stars told an undeniable truth. There was something massive and compact at the galactic centre, something invisible yet irresistible. As the observations continued, new details emerged. The orbits weren't random, they were precise ellipses, just as Newton's laws predicted, but slightly distorted by relativistic effects. The closer a star came to the centre, the more space-time itself bent beneath its feet. Light from those stars shifted toward the red, stretched by gravity's grip. Time for them slowed compared to time for us. It was Einstein's theory of general relativity playing out in real time, written across the sky in the motion of distant suns. Every frame of that stellar choreography was a triumph of patience and precision. It took more than 20 years of uninterrupted monitoring, dozens of scientists, and thousands of nights at telescopes to build a clear picture. But when they finally connected the dots, the result was breathtaking. The stars were orbiting a single compact object containing about 4 million times the mass of the Sun, confined to a space no larger than our solar system. There was no other explanation. Sagittarius A star was indeed a supermassive black hole. The implications were profound. For the first time, humanity had not only detected a black hole but measured its effect with exquisite accuracy. The galactic core was no longer a mystery. It was a laboratory for the most extreme physics in existence. Every orbiting star became a probe of gravity, a messenger from the edge of the abyss. And as telescopes grew sharper and computers more powerful, those measurements would reveal even more: the bending of light, the warping of time, the precise shape of space-time itself. The dancing stars of the Milky Way had unveiled the secret long hidden in the dark. They had shown us that our galaxy, for all its beauty and serenity, revolves around a monster. Yet there was a strange comfort in that revelation. It meant that the chaos had order, that the vast machinery of the cosmos moved in harmony with laws that even a black hole must obey. The stars had danced their truth into the light, and in doing so they had brought the invisible into view. Among all the stars orbiting near Sagittarius A star, one became the centerpiece of modern astrophysics, a single brilliant speck known as S2. This star, hot and blue-white, races around the galactic center in a breathtaking elliptical orbit that carries it closer to a supermassive black hole than any other known object of its kind. Its journey lasts just 16 years, a cosmic heartbeat compared to the age of the universe, yet during that time it travels hundreds of billions of miles, tracing a perfect loop through the warped space around the Milky Way's heart. At its closest approach, S2 plunges to within just 17 light hours of the black hole, roughly 3 times the distance between Pluto and the Sun. In human terms, that is unimaginably close. At that distance, the gravity of Sagittarius A star bends space like a lens and slows time itself. During that brief, perilous moment of closest passage, S2 streaks through space at over 17 million miles per hour, nearly 3% of the speed of light. To observers on Earth, it becomes a living laboratory, a chance to test Einstein's general relativity, not in equations or thought experiments, but in the raw reality of motion. Astronomers followed S2's path for more than 2 decades, tracking it with incredible precision using adaptive optics that compensated for the distortion of Earth's atmosphere. Each data point was a note in a cosmic symphony, revealing how space and time behave under the influence of an immense gravitational well. When S2 approached the black hole in 2018, telescopes around the world focused on it like never before. The star's light shifted noticeably toward the red, stretched by the black hole's gravity in a phenomenon known as gravitational redshift. It was the first time such an effect had ever been directly observed around a supermassive black hole, and it matched Einstein's predictions perfectly. The event was more than a triumph of science. It was a moment of awe. Humanity had watched the universe bend light and time, with the precision of mathematics written into the fabric of reality. S2 became more than a star. It became a messenger, carrying evidence from a place where the ordinary rules of nature dissolve. Its orbit revealed not only the mass of Sagittarius A star, about 4 million suns, but also how sharply concentrated that mass must be. No cluster of stars, no collection of exotic particles could mimic the gravitational field required to accelerate S2 to such extremes. The black hole was the only answer that fit. And yet, S2's journey told an even deeper story. Every time it completed an orbit, the shape of its path shifted slightly, rotating in a pattern known as precession. This tiny wobble, predicted by general relativity, arises because space-time itself is curved, and orbits around such curvature can never close perfectly. The effect had been measured before for Mercury around our Sun, but here it unfolded on a scale millions of times greater, in a gravitational field far more intense. It was like watching Einstein's equations come alive against the background of eternity. When astronomers plotted the data, they saw the orbit trace a rosette, a delicate flower-shaped pattern blooming in the heart of the galaxy. Every petal represented another dance around the black hole, each one slightly offset from the last. To the human eye, it was beautiful. To science, it was irrefutable proof that space and time were bending exactly as relativity demands. Observing S2 also opened a window into the behavior of matter near the edge of the possible. As the star swung around the black hole, tidal forces stretched it slightly, tugging at its atmosphere. The light it emitted flickered and dimmed, not from instability, but from the extreme conditions it endured. It was a star surviving at the frontier between existence and oblivion. Studying it taught us how stars can form, evolve, and persist even in the most hostile environments. The galactic centre, once thought too violent for life of any kind, proved to be full of surprises, stars like S2 thriving in orbits where logic once said nothing could remain intact. For humanity, the discovery carried a quiet poetry. We had found a star that dances with a black hole and survives. Each orbit it completes tells a story of endurance and order within chaos. Its path is a thread connecting us to the deep geometry of the universe, showing that even in the heart of darkness, there is rhythm, there is law, there is beauty. S2 reminds us that the universe is not random. It is structured, deliberate, elegant. The same equations that keep Earth in orbit around the Sun also guide this star as it skirts the edge of eternity. And as long as S2 continues its silent journey around Sagittarius A star, it will remain a symbol of humanity's relentless pursuit of understanding, a reminder that even in the darkest places, the cosmos still dances. Once astronomers had traced the orbit of S2 and its stellar companions, the time had come to weigh the invisible. To measure a black hole is to measure gravity itself, and doing so requires extraordinary precision. Every curve of a star's orbit, every change in its velocity, carries within it the fingerprint of the mass that pulls it. By studying these motions in detail, scientists could finally calculate exactly how heavy Sagittarius A star truly is, and, just as importantly, how small the space is that contains that weight. The results were staggering. Using the data collected over 2 decades, researchers determined that the object at the centre of our galaxy possesses roughly 4 million times the mass of the Sun. Yet all of that mass is confined to a region no larger than the solar system. No other known form of matter could fit such density without collapsing. This was the definitive proof. The Milky Way's heart is ruled by a supermassive black hole, a single gravitational titan holding the galaxy in its invisible grip. But the process of weighing it was a triumph of both mathematics and technology. Astronomers used Kepler's laws of motion as a foundation, then layered Einstein's corrections on top to account for relativistic effects. The stars near the galactic centre do not simply follow classical orbits. Their paths twist and shift as space-time itself bends under the black hole's influence. This meant every equation had to include not only position and velocity, but also time dilation, redshift and gravitational lensing. The calculations became a delicate symphony of physics, with every note contributing to the final number. 4.3 million solar masses. That figure gave humanity a new sense of scale. To imagine it is to imagine compressing 4 million suns into a single point and entity so dense that even light cannot escape. The gravitational pull at its event horizon is beyond comprehension. A particle of dust, if it crossed that threshold, would be trapped forever, its existence erased from the universe's record except as a tiny addition to the black hole's mass. And yet, the influence of that mass extends across the Milky Way, subtly guiding the orbits of countless stars like an invisible conductor, keeping time in a cosmic symphony. Measuring Sagittarius A star was not just an act of observation, it was a declaration of understanding. Humanity had confirmed that the same equations governing an apple's fall on Earth could also describe the motion of stars around a singularity. Newton's gravity had evolved through Einstein's relativity into a unified language of motion, and the galaxy itself had become the ultimate laboratory. As instruments improved, measurements grew even more precise. The Very Large Telescope in Chile, equipped with adaptive optics and interferometry, allowed scientists to pinpoint stellar positions to within milliseconds, the equivalent of spotting a coin on the Moon from Earth. Combined with radio observations from the Event Horizon Telescope, this precision turned the galactic core into the most closely studied region of space outside our solar system. Each year, astronomers watched the stars trace their paths, refining their estimates, and confirming again and again that the mass of Sagittarius A star remained constant. No other explanation fit. A cluster of neutron stars would scatter. A ball of dark matter would evaporate. Only a black hole could endure. The certainty was complete, and with that certainty came a shift in perspective. For centuries, black holes had existed only as abstract monsters' mathematical curiosities or symbols of cosmic doom. Now they were measurable, predictable, even familiar. They were no longer metaphors. They were real entities, governed by physics as elegantly as planets or stars. The invisible had become tangible through mathematics alone, yet there was humility in that achievement. Even with its mass precisely known, the interior of a black hole remains an enigma. The equations break down at the singularity, where density becomes infinite and time ceases to have meaning. The laws we use to measure the universe stop working in that place. It is a reminder that while we can calculate the shape of space-time, we still do not know what happens at its limits. Measuring the monster revealed both our power and our ignorance. We had weighed the unseeable and found its number, yet the nature of its core remains forever out of reach. Still, that act of measurement was one of humanity's greatest triumphs. To take the faint motions of distant stars and translate them into knowledge about the deepest abyss in our galaxy is nothing short of extraordinary. In doing so, we confirmed that our place in the universe is not defined by fear of the unknown, but by the drive to understand it. Sagittarius A star became more than an astronomical object. It became a symbol of human curiosity, a silent reminder that even the darkest places yield their secrets to those who persist in seeking them. For generations, Sagittarius A star was known only through its gravity, a ghostly presence that could bend the paths of stars yet remain unseen. We could measure it, infer it, even predict its behavior, but no one had ever looked directly into its face. A black hole, by definition, emits no light. To see it meant doing the impossible, capturing an image of darkness itself. Yet scientists dared to try. The dream of photographing a black hole began as early as the 20th century, when theorists realized that while nothing can escape a black hole's grasp, the light swirling around it might leave a visible signature. Matter falling toward the event horizon forms an accretion disk, heating to incredible temperatures and glowing brightly before disappearing forever. From Earth, this would appear as a glowing ring surrounding a dark center, the shadow cast by gravity on the fabric of space. To capture that image required technology and collaboration on a scale unlike anything before. The Event Horizon Telescope, or HT, was born from that ambition. It wasn't a single telescope, but a network of observatories scattered across the globe, from Hawaii to Chile, from Spain to the South Pole, all synchronized to function as one enormous eye the size of Earth itself. This technique, called very long baseline interferometry, allowed astronomers to achieve the angular resolution necessary to distinguish details smaller than a grain of sand on the moon. But achieving that precision was a monumental challenge. Each telescope had to record vast amounts of data with atomic clock accuracy, storing petabytes of information that would later be combined and processed at supercomputing centers. The atmosphere, the rotation of the planet, even the smallest timing error could distort the signal. For years, scientists refined the methods, calibrated the instruments, and waited for the right conditions to align. Before targeting Sagittarius A star, they turned their attention to another black hole, one even larger and easier to capture, the giant at the center of the galaxy M87. In 2019, the world watched in astonishment as the first image of a black hole was revealed, a glowing orange ring encircling a dark void, the unmistakable shadow of the event horizon. That image changed the course of science and imagination forever. It proved that Einstein's theory held true at the very edge of the possible. Yet even as humanity celebrated, one goal remained: the black hole in our own backyard. Sagittarius A star posed a far greater challenge. Unlike M87's colossal black hole, which is stable and slow-moving, Sagittarius A star is small and dynamic. Its hot gas whirls around in minutes rather than days, constantly changing brightness and structure. To capture a clear image of such a restless object would be like photographing a firefly from across the world during a hurricane. But the EHT team persisted. They gathered data for years, refining algorithms that could reconstruct an image from signals scattered across time and distance. Every photon captured was a clue, every interference pattern a whisper from the edge of space-time. The work required not just science, but artistry, a balance between data and interpretation, between precision and imagination. Finally, in 2022, the image was unveiled. On screens around the world appeared a glowing, donut-shaped ring of light, orange and blurred, yet unmistakably circular, with a dark center at its heart. It was the shadow of Sagittarius A star, the first direct evidence of the black hole that anchors the Milky Way. Humanity had seen the unseeable. For a moment, the abstract became real. The equations of relativity, the decades of measurements, the orbits of S2 and its companions, all of it culminated in that single image. It was not sharp or colourful, not cinematic like science fiction, but it was profoundly human, a picture born of patience, cooperation and curiosity stretched across continents. The dark centre was not the black hole itself, but its silhouette, carved into light by gravity. Around it, photons raced in tight orbits, some looping multiple times before escaping. Every pixel of that image represented light bent through space and time, a map of distortion sculpted by an object that defies existence. The image confirmed what theory had long suggested. The mass, size, and spin of Sagittarius A star matched predictions almost perfectly. It proved that our galaxy's heart is indeed a supermassive black hole, 4 million suns compressed into a single invisible point. But beyond the science, the moment carried something deeper, the realization that we had glimpsed the boundary between being and nothingness. In that faint orange ring, humanity saw the shadow of creation's limits. The Event Horizon Telescope had not only achieved a scientific milestone, it had captured a symbol of our place in the universe. The invisible had been brought into sight, not by divine light, but by the persistence of human vision. To see a black hole is to see the edge of physics, the edge of understanding, the edge of everything. And now the universe had shown us its most guarded secret, the face of the abyss that holds us all in orbit. The image of Sagittarius A star revealed a ring of fire suspended in nothingness, a glowing circle surrounding an endless shadow. It was unlike any photograph humanity had ever taken, not because of its clarity, but because of what it represented. That faint, flickering halo was light trapped in orbit, radiation born from chaos, bent and twisted by gravity until it curved back upon itself. To look at it was to stare directly at Einstein's equations made visible, the warping of space-time rendered as art. The ring's glow did not come from the black hole, but from the matter spiralling toward it. As gas and dust fell inward, friction and compression heated them to billions of degrees, forcing atoms to shed their energy as radiation. The result was a luminous storm of plasma, moving so fast that it circled the black hole in mere minutes. Magnetic fields twisted through it, shaping jets and arcs of light that flickered in rhythmic pulses. The ring appeared uneven, brighter on one side, dimmer on the other. That asymmetry was not a trick of the telescope, but a signature of relativity itself. The side moving toward us glowed more intensely because its light was boosted by motion near the speed of light, a phenomenon called relativistic beaming. The opposite side, moving away, faded into shadow. In that contrast lay proof of Einstein's theory. Space was not passive, but dynamic, bending and stretching under the weight of mass and energy. Every photon that reached the Event Horizon Telescope had travelled through a labyrinth of warped geometry, looping and twisting before escaping to tell its story. The fiery ring was a message across 26,000 light-years, a postcard from the edge of forever. Yet what we see in that image is only the surface of the truth. Beneath the glowing plasma lies the event horizon, the point where escape becomes impossible. Beyond it, the pull of gravity grows so absolute that even light cannot find its way out. This boundary is not a physical surface, but a threshold in space-time, the edge between the observable and the unknowable. The dark centre in the image is the shadow cast by that boundary, a silhouette against the luminous fury surrounding it. That shadow is larger than the black hole itself because the intense gravity bends light around it, enlarging the darkness like a distorted reflection. It is this illusion that allows us to see what cannot be seen. The fiery ring is the final scream of matter before it disappears forever, the visible evidence of energy's surrender to gravity. To the untrained eye, The image may appear simple, almost abstract, a blurred circle of orange light fading into black. But to physicists, it is a triumph of both theory and observation. It matches models predicted by general relativity to within a few percent, confirming once again that Einstein's description of the universe remains unbroken even in its most extreme conditions. That single photograph contains the curvature of space-time, the flow of magnetic fields, the heat of collapsing atoms, and the echo of light trapped in an endless whirlpool. It is both science and poetry in one frame. The accretion disk itself is a place of violent beauty. Within it, particles collide at nearly the speed of light, generating shock waves and bursts of X-rays that ripple outward. The heat and motion within this disk are so intense that if it were visible to the human eye, it would outshine every star in the sky. Yet from our distant vantage point, it appears serene, like a ring of molten gold suspended in eternal stillness. Time near the event horizon moves differently. A second there can stretch into minutes or hours for an outside observer. Were we to watch a single particle fall inward, we would see it slow, dim, and fade, never quite crossing the boundary. To us it would seem frozen in time, eternally approaching but never arriving. This illusion, too, is part of the black hole's strange elegance and object that consumes, yet from our perspective, never quite finishes the act. The fiery ring is a paradox made visible, chaos and symmetry, destruction and creation, silence and fury coexisting at the same point in space. It is the boundary where the known laws of physics surrender to something deeper, something we do not yet understand. Looking at that image, one cannot help but feel a sense of reverence. It is not just a scientific achievement, it is a mirror held up to the cosmos, showing us the beauty of the universe's most terrifying truth. That in the heart of darkness, there is order, that even the void can shine. The fiery ring of Sagittarius A star is not merely a photograph, it is a reminder that the universe still has secrets grand enough to humble us, and that light itself will always find a way to reveal them. Among the countless suns orbiting the centre of the Milky Way, one shines brighter, moves faster, and defies more limits than any other. It is the star called S2, the same cosmic dancer that helped reveal the existence of Sagittarius A star. Yet S2's significance goes far beyond proof of the black hole's mass. It is a living experiment, a celestial test particle allowing scientists to observe the raw effects of gravity at its most extreme. Every time S2 sweeps through its orbit, the universe writes another line of the story of relativity. Its journey is one of incredible violence and grace, a marathon of survival in the heart of a gravitational storm. S2's orbit takes 16 years to complete, and for most of that time it travels through relative calm, far from the black hole's suffocating pull. But when it reaches pericenter, the point of closest approach, it enters a domain where the rules of reality begin to warp. In 2018, astronomers observed S2 as it made one of these close passes. For a brief moment, the star came within just 17 light-hours of Sagittarius A star, a cosmic hair's breadth on a galactic scale. At that distance, it was moving at a staggering 17 million miles per hour, fast enough to circle Earth 7 times in a single second. No other known star in the galaxy has been clocked at such velocity. But what truly fascinated scientists wasn't just its speed, it was how its light changed as it approached and receded. The gravitational field of the black hole stretched S2's light into longer wavelengths, a phenomenon known as gravitational redshift. For the first time, astronomers could directly measure this effect around a supermassive black hole, confirming one of Einstein's most daring predictions. It wasn't theory anymore, it was observation. As S2 dove toward the abyss, time for the star itself slowed relative to us. Every pulse of its light reached our telescopes slightly delayed, every second elongated by gravity's invisible hand. From our perspective, it was as though the star's clock had begun to tick more slowly. This wasn't illusion, it was reality. The closer one moves to a black hole, the more space-time itself stretches, distorting the flow of time. S2 allowed us to see this happen not in distant theory, but in our own galaxy, under our own observation. Watching it was like watching the fabric of the universe ripple in slow motion. The data gathered from S2's orbit confirmed that general relativity holds true even under the crushing weight of a supermassive black hole. The equations worked flawlessly. No deviation was found. But with confirmation came curiosity. If Einstein's laws held so perfectly here, might they eventually break down somewhere deeper inside, closer to the singularity? Could S2, or a future discovery like it, reveal where the seams of physics begin to tear? Those questions remain open, yet S2's role continues to grow. Its orbit isn't static, it precesses, meaning each cycle traces a slightly different path, slowly rotating around Sagittarius A star. This precession, caused by space-time curvature, mirrors the same phenomenon observed in Mercury's orbit around the Sun but magnified by millions of times. Each revolution adds another data point, another layer of evidence that the universe bends as Einstein described. SS2's movements also help refine our understanding of the black hole's spin, how fast it rotates, how its rotation drags space-time around with it, in a process known as frame dragging. By measuring subtle shifts in S2's path, scientists can map how the black hole twists the very geometry of reality. These are not small questions, they touch the deepest foundations of physics. And yet, S2 remains, at its core, a single star doing what stars have done for billions of years, moving, burning, existing. Its brilliance is not in what it is, but in what it reveals. Through its orbit, we glimpse truth that can't be replicated in laboratories or written in chalk. We see time stretch. We see light bend. We see gravity transform from a familiar pull into an architect of space-time itself. S2 is a messenger, one that speaks in the language of motion. It tells us that even in the depths of a gravitational abyss, order persists, and that the universe, for all its complexity, still obeys the rules it has written for itself. When S2 swings closest to the black hole, its light flickers with a strange beauty, a combination of Doppler shifts, gravitational distortion, and sheer velocity blending into one symphony of physics. For those few moments, it is the fastest-moving, most extreme star known to humankind, a symbol of both fragility and endurance. It survives the unimaginable, orbit after orbit, blazing a trail through curved space. In doing so, it reminds us that even on the very edge of eternity, motion continues, light persists, and time, though stretched and twisted, never truly stops. To understand what happens near a black hole is to question what time itself means. In everyday life, time feels constant, unchanging, ticking forward at the same rhythm for all. Yet near Sagittarius A star, time behaves differently. It stretches, slows, and twists, molded by gravity like clay. This phenomenon, called gravitational time dilation, is not science fiction. It is a measurable reality, and S2's journey around the black hole allowed humanity to witness it unfold in real time. Einstein predicted more than a century ago that gravity and time are inseparable. The stronger the gravitational field, the more space and time curve, and the slower clocks tick. To an observer far from the black hole, a second near the event horizon appears longer, stretched by the immense gravity that warps space-time. Conversely, to someone falling inward, nothing unusual seems to happen. Their own clock keeps perfect rhythm. Both perspectives are correct, each confined within its own warped reality. This paradox defines the very nature of a black hole. It is not just a place where light is trapped, but a place where time itself becomes distorted beyond recognition. When S2 reached its closest point to Sagittarius A star, the star's light bore the signature of this effect. As it plunged through the curve of space-time, the frequency of its light shifted toward red, as though stretched by invisible hands. That redshift was a direct translation of time dilation into observable data. To us, watching from Earth, S2's heartbeat slowed, its seconds expanded. Yet for S2 itself, time flowed normally. It was as if the universe had two clocks, each keeping time according to its own gravity. This realization forces us to reconsider what now even means. In the presence of a black hole, simultaneity dissolves. Two observers may exist within the same universe, yet experience completely different rates of time. The closer one moves to the event horizon, the more pronounced the difference becomes. At the very edge, time for an outside observer stops entirely. A falling object would appear to freeze in place, fading slowly from view as its light redshifts into invisibility. But from the falling object's own perspective, it crosses the boundary and continues onward, unaware of the divide. This is the strange poetry of relativity. Reality depends on where you stand. Time is not universal, it is personal. Near Sagittarius A star, the warping of time is not a metaphor but a force as real as gravity itself. Even the black hole's immense influence over the Milky Way is bound by this stretching of temporal fabric. The entire galaxy moves to its rhythm, orbiting a center where time runs differently than anywhere else. If we could somehow travel there and look outward, we would see the universe in fast motion, stars aging rapidly, cosmic events unfolding at impossible speed. For the black hole, the outside universe races ahead. For us, the black hole's clock drags eternally. This duality challenges our intuition. We think of the universe as sharing one timeline, but in truth, it is a web of countless personal times woven together by gravity. The black hole merely exposes the extremes of that truth. In a sense, Sagittarius A star is not just the center of our galaxy, it is the galaxy's timekeeper, the point where temporal flow bends most dramatically. What happens there is a reminder that time is not something separate from space, but part of a single elastic fabric that can stretch, twist, and even tear. The warping of time also reveals something deeper about our place in the cosmos. Every gravitational field, no matter how small, slows time just a little. The stronger the gravity, the greater the effect. That means even on Earth, time runs slightly slower at sea level than on the top of a mountain, because the planet's gravity is stronger closer to its core. GPS satellites orbiting high above must constantly correct for this difference, or navigation would drift by miles each day. We live within a constant but subtle curve of time, unaware of how malleable it truly is. Sagittarius A star simply magnifies this truth to an extreme that makes it undeniable. The star S2 gave us proof, but the concept touches every corner of existence. Time is not fixed. It bends under weight. It yields to gravity's command. In that revelation lies both wonder and humility. The universe does not tick to a single rhythm. It sings in a spectrum of tempos, from the slow heartbeat of a black hole to the frantic hum of radiation speeding through space. Each object moves through its own stream of time, intersecting with others in a dance too vast to fully comprehend. Near the center of our galaxy, where the flow of seconds thickens and the edge of eternity lies just beyond reach, time ceases to be a backdrop and becomes a living, breathing dimension. There, in the warped light of Sagittarius A star, the universe teaches us that even time, the one constant we thought we understood, is merely another player in the grand cosmic symphony. When scientists began tracking the star S2 and its neighbors for decades, they noticed something subtle, something that revealed another secret of the black hole's nature. The orbits weren't closing in perfect ellipses as Newton's equations would suggest. Each time S2 completed its 16-year journey around Sagittarius A star, the ellipse had rotated slightly, its point of closest approach shifting forward. Over time, this pattern created a delicate rosette shape, a cosmic flower blooming in the darkness of the galactic core. This was not random motion or measurement error, it was the unmistakable mark of general relativity in action. In the Newtonian view, an orbit is a simple dance. A planet moves around a central mass in an unchanging oval, returning again and again to the same point. But in the real universe, where space itself bends and flexes under the influence of gravity, those paths do not repeat exactly. Instead, the geometry of space-time causes them to precess, rotating slowly like the petals of a flower, unfurling in invisible wind. Mercury's orbit around the Sun shows this effect on a small scale, its ellipse shifting by a fraction of a degree each century due to the Sun's gravity warping the nearby fabric of space. But near Sagittarius A star, that warping is magnified millions of times. The precession of S2's orbit is not measured in fractions. It's a visible, measurable movement, a direct demonstration of how space-time curves near a supermassive black hole. For physicists, this was exhilarating. The Rosette orbit was not just a visual metaphor, it was data, hard evidence that Einstein's predictions held true even in the most extreme gravitational environment humanity could observe. When astronomers mapped S2's motion, they found the precession matched the amount predicted by relativity with astonishing precision. Every shift, every curve, Every deviation from a perfect ellipse confirms that space around the black hole is not static. It is dynamic, warped, and alive. To understand what causes this precession, one must imagine space-time as a vast elastic sheet. A small mass, like a planet, creates a shallow dimple, and an orbiting object moves smoothly around it. But a massive body like Sagittarius A star creates a deep, spinning whirlpool that distorts everything nearby. As S2 moves through this curved region, it experiences slight changes in the gravitational pull depending on its position. Each orbit therefore doesn't close on itself but shifts forward, tracing a spiral pattern that slowly winds around the black hole. This phenomenon, called Schwarzschild precession, is one of the purest signatures of general relativity. Observing it around a supermassive black hole is equivalent to seeing the theory carved into the fabric of the universe. But there's another layer to this story rotation. If Sagittarius A star spins, as most black holes do, then it drags space-time around with it, twisting the geometry like a spinning spoon stirring honey. This effect, known as frame dragging, adds another subtle nudge to S2's motion. Over centuries it could alter the orientation of entire orbits, aligning or scattering stars according to the black hole's spin. Detecting that influence is the next frontier, a challenge that will test the limits of human precision and patience. The Rosette orbit is more than just a scientific curiosity, it's a visual symphony of physics. When astronomers animate the data, S2's path becomes a glowing loop spinning gracefully around an invisible center, each path slightly offset from the last. Together, these loops form a luminous flower of motion, a natural pattern that merges beauty with mathematics. It is a reminder that even the harshest environments of the cosmos obey a deep order, an underlying symmetry hidden within apparent chaos. This dance of geometry extends far beyond one star. Other stars near the galactic center show similar behavior, each tracing its own shifting ellipse, each adding another note to the melody of space-time. Over thousands of years, these combined precessions may alter the structure of the entire central cluster, shaping the orbits of new stars born from the surrounding gas. In this way, the black hole not only dictates gravity, it writes the choreography of creation itself. To see the Rosette orbit is to witness the universe thinking in curves. It's a manifestation of a truth Einstein revealed a century ago, that gravity is not a force pulling objects together, but the natural motion of bodies following the bends and folds of space-time. What we perceive as attraction is really geometry in motion, and the Rosette is its signature. Every orbit, every precession, every shimmering path through the galactic core is a message written in the language of curvature. The black hole does not shout its presence, it whispers through the stars it commands. Each flower-shaped orbit around Sagittarius A star is a silent proof, a glowing affirmation that the universe is governed by laws both elegant and unyielding, and in that grace, in that precise distortion of motion, humanity finds a mirror evidence that even in the most chaotic corners of existence, beauty and order endure. When most people think of black holes, they imagine insatiable monsters devouring everything that comes close, engines of destruction, swallowing stars whole. Yet Sagittarius A star, the supermassive black hole at the center of our galaxy, behaves in a surprisingly gentle way. Compared to the violent quasars and blazing cores of distant galaxies, our own galactic heart is remarkably calm, a quiet giant rather than a raging beast. It rests in a delicate balance between hunger and restraint, feeding only on scraps of matter that drift too close. Understanding this temperament, this strange cosmic calm, has become one of the most intriguing puzzles in modern astrophysics. The black hole at the Milky Way's center is capable of unimaginable violence. It possesses the energy to shred planets, vaporize stars, and hurl jets of radiation across light years, yet it rarely does. For the most part, Sagittarius A star simply waits, patient and still, surrounded by a faint swirl of hot gas and dust that never quite falls in. Astronomers once expected to find a roaring quasar in our galactic core, a brilliant engine lighting up the sky. Instead, they discovered a whisper-faint radio and X-ray flares, punctuating long stretches of silence. The reason lies in how the black hole consumes matter, or rather how it fails to. When gas and dust approach the event horizon, they form an accretion disk spiraling inward and heating to immense temperatures. In some black holes, this process is ferocious, converting matter into light with astonishing efficiency. But Sagittarius A star is different. Much of the material near it is ejected before it ever crosses the boundary, flung away by powerful magnetic fields and turbulent winds. In other words, it's a messy eater. The same forces that draw matter in also blast it back out, creating a self-regulating system that limits the black hole's appetite. The result is a remarkably low rate of accretion, so little that the light it emits is millions of times weaker than the blazing hearts of active galaxies. It is, by cosmic standards, starving. Still, it is not lifeless. Occasionally something drifts too close, a clump of gas, a fragment of a star, a comet-sized object, and the black hole stirs. It flares suddenly, brightening in X-rays and infrared light for a few minutes or hours before settling back into slumber. These outbursts are the black hole's heartbeat, flashes of activity revealing its underlying power. When telescopes catch one of these flares, scientists glimpse the boundary between calm and chaos, the moment when gravity and magnetism collide in violent harmony. Sagittarius A star's quiet nature also helps preserve the fragile environment around it. The galactic center is crowded with stars, gas clouds, and young stellar clusters, all packed into a volume barely a few light-years across. If our black hole were more active, its jets and radiation would sterilize this region, stripping away material that forms new stars. But its restraint allows the area to remain fertile, paradoxical garden of creation in the shadow of annihilation. This balance between dormancy and power is part of what makes Sagittarius A star so fascinating. It embodies the duality of black holes, the power to destroy and the role of cosmic architect. When black holes feed vigorously, their radiation shapes galaxies, regulating star formation by heating or dispersing gas. When they sleep, gravity quietly molds the galactic structure, keeping billions of stars in stable orbits. In both states, they control the evolution of everything around them. Sagittarius A star may seem tame, but its influence is profound. It acts as the Milky Way's stabilizer, a gravitational anchor that holds the galaxy's disk in its elegant spiral shape. Without it, the orbits of stars could drift chaotically over billions of years. The black hole's mass creates a steady gravitational center, maintaining the order of the cosmic dance. Its silence, therefore, is not weakness, but control. Astronomers sometimes describe Sagittarius A star as underfed, but perhaps that's the wrong metaphor. It is not starving, it is selective. It consumes only what the universe offers naturally, never forcing its feast. That quiet discipline makes it an exceptional subject of study. We can observe its every flicker without being blinded by overwhelming light, something impossible in galaxies with raging quasars. Each small flare is like a heartbeat in the dark, a reminder that even in its stillness, immense power sleeps beneath. And so the black hole's temperament teaches us something profound. Not all cosmic giants express their power through destruction. Some express it through balance. The true strength of Sagittarius A star lies not in how much it devours, but in how perfectly it governs its domain. It is a monarch of gravity that rules without rage, commanding the Milky Way not through violence, but through quiet inevitability. In its patience we see endurance. In its silence we find stability. And in that restraint, the universe reveals that even its mightiest forces can exist in peace. Sagittarius A star is not just a passive anchor at the center of the Milky Way. It is the quiet architect of the galaxy's entire structure. Its gravity sculpts the spiral arms, shapes the flow of interstellar gas, and orchestrates the grand design of our cosmic home. Every star that orbits within the galaxy, from the ancient giants near the core to the newborn suns in the outer rim, owes its motion and stability to the gravitational blueprint drawn by this invisible engineer. Though silent and unseen, Sagittarius A star has played a central role in the formation, evolution, and ongoing rhythm of the Milky Way. To understand its influence, we must see the galaxy not as a static collection of stars, but as a living system, a vast rotating disk of matter bound together by gravity. At the center of this rotation lies the black hole, a point of extreme density that anchors the motion of everything else. Without such a gravitational heart, the Milky Way's spiral arms could not maintain their elegant form. They would drift apart over billions of years, their pattern dissolving into chaos. Instead, they remain coherent, sustained by the steady gravitational pull of the black hole and the halo of dark matter that surrounds it. The spiral structure itself is a manifestation of order emerging from gravity's guidance, a frozen wave, a cosmic echo of the forces that built the universe. Sagittarius A star also influences how stars are born and where they thrive. Near the galactic center, its immense gravity compresses gas clouds into dense filaments, triggering bursts of star formation. Yet at the same time, its occasional flares and winds can blow material away, halting that process. It is a sculptor that carves and creates simultaneously, shaping the environment through both pressure and release. The result is a delicate equilibrium, regions of furious creation alongside zones of stillness, like alternating notes in a cosmic rhythm. Over the lifetime of the galaxy, this balance has defined the Milky Way's character, neither too chaotic nor too static, neither barren nor overgrown. The black hole also exerts an unseen hand through its magnetic influence. The plasma swirling near the event horizon generates powerful magnetic fields that stretch for light years, threading through the galactic core like invisible filaments. These magnetic lines shape the motion of charged particles, guiding cosmic rays and influencing the alignment of gas flows throughout the central bulge. Observations have revealed vast magnetic structures extending hundreds of light-years above and below the plane of the galaxy, forming loops and arcs that rise like luminous ribbons in radio wavelengths. They are evidence of the black hole's reach, a reminder that even when dormant, it continues to sculpt the environment around it. The role of Sagittarius A star as a galactic architect extends beyond its immediate surroundings. When black holes feed, their energy output can regulate the growth of entire galaxies, a process known as feedback. During its more active phases in the distant past, our black hole may have released powerful outbursts that shaped the Milky Way's evolution. Astronomers have discovered giant bubbles of gas extending tens of thousands of light-years above and below the galactic plane, known as the Fermi bubbles, believed to be remnants of a massive explosion from Sagittarius A star millions of years ago. Those colossal outflows likely cleared away gas from the central regions, influencing where new stars could form. Even now, long after the storm has faded, the imprint of that ancient event remains etched into the Milky Way's structure. This duality, creation and destruction, is what defines the black hole's role as an architect. It can both ignite and extinguish, both sculpt and erase, and yet its influence is not violent in the way we might imagine. It operates over cosmic timescales, changing the galaxy slowly but profoundly, like an artist shaping clay over millennia. To the human eye, the Milky Way appears eternal and serene, but behind that stillness lies motion, rotation, collapse, expansion. All choreographed by the unseen hand at the center. The idea that a single, invisible object could determine the fate of hundreds of billions of stars is almost too vast to comprehend. Yet that is the quiet truth of our galaxy's existence. Sagittarius A star is the keystone in an immense gravitational arch. Remove it, and the Milky Way would unravel. Leave it in place, and order persists. This relationship between the galaxy and its black hole is one of cosmic balance, the creator and the created, locked in perpetual harmony. When we look up at the night sky and trace the soft band of the Milky Way stretching across the darkness, we are witnessing the legacy of that balance. Every shimmer of starlight is part of a grand design shaped by gravity's architect. Though hidden behind dust and shadow, Sagittarius A star continues its silent work, steady, patient, eternal sculpting the galaxy, not through destruction, but through the simple, enduring act of keeping everything bound together. At the heart of the Milky Way, surrounding Sagittarius A star, lies one of the most extraordinary regions in the entire galaxy, a place so dense, so energetic, and so chaotic that it defies every image of serene starlight we associate with the night sky. This is the galactic core, a sphere only a few light-years across, crammed with millions of stars, stellar remnants, and clouds of superheated gas all orbiting the supermassive black hole in a kind of controlled frenzy. If we could stand there, somehow immune to radiation and tidal forces, the sky would never be dark. It would blaze with light from every direction, stars so close together that shadows could never exist. The core is a cosmic city that never sleeps. The stars that populate this crowded environment are unlike those in our quiet neighborhood of space. Many are massive, young and volatile, burning through their fuel in just a few million years before exploding as supernovae. Others are ancient survivors, compact remnants such as white dwarfs, neutron stars, and smaller black holes left over from earlier generations. They coexist in a gravitational battleground, orbiting at hundreds or even thousands of kilometers per second, each tracing a complex path through curved space-time. The closer to Sagittarius A star one goes, the faster and wilder the orbits become. These extreme conditions produce interactions rare anywhere else in the galaxy close encounters, collisions and mergers between stars. Some pairs become binary systems locked in mutual orbit, while others are torn apart, flinging one star outward while the other plunges toward the black hole. These stellar slingshots can accelerate stars to incredible speeds, sometimes fast enough to escape the galaxy entirely. Such hypervelocity stars are cosmic refugees, ejected from the Milky Way by the gravitational chaos of the core. Yet despite this turbulence, life continues to flourish here in its own way. The galactic centre is a nursery as much as a graveyard. Vast clouds of molecular gas swirl through the region, compressed by tidal forces into dense pockets that ignite new generations of stars. It's a paradox. One of the most hostile environments in the galaxy is also one of its most prolific birthplaces. Some of the stars orbiting closest to Sagittarius A star within a few light days are astonishingly young, just a few million years old. How they formed in such extreme conditions remains one of astronomy's enduring mysteries. The tidal forces near the black hole should tear gas clouds apart before they can collapse into stars. And yet, somehow, nature finds a way. Some theories suggest these stars formed farther out and migrated inward through gravitational interactions. Others propose that massive disks of gas once orbited the black hole and fragmented, giving birth to stars directly within its gravitational grip. Whatever the mechanism, their existence challenges our understanding of how stars are born and survive under such crushing conditions. Beyond the stars themselves, the galactic core is home to structures of pure wonder, filaments of plasma stretching for light years, glowing in radio waves like cosmic lightning bolts. These filaments are shaped by magnetic fields twisted by the black hole's spin, marking invisible lines of force threading through the region. They act as conduits of energy, channeling particles and radiation in ways we're only beginning to comprehend. At larger scales, the black hole's influence extends to clusters of intermediate mass black holes, remnants of smaller galaxies consumed by the Milky Way in its past. These ghostly companions drift through the core like silent satellites, occasionally merging or disturbing nearby stars. Each merger releases gravitational waves, ripples in space-time that echo across the galaxy. One day, detectors sensitive enough to hear them will listen to that deep cosmic hum, the background music of the Milky Way's beating heart. The crowded core is not chaos without meaning. It is order at the edge of instability, a place where gravity, magnetism, and energy balance on a knife's edge. Every explosion, every orbit, every collision contributes to a larger equilibrium. The black hole's gravity maintains that balance, keeping the chaos contained. Without it, the region would dissipate. With it, it thrives. To observe the galactic core is to watch creation and destruction unfold in the same breath. It is a place where stars are born beside the remnants of others long dead, where time itself flows differently, and where the light of countless lives blends into one shimmering brilliance. This region, unseen by human eyes yet mapped by radio and infrared vision, is the living heart of our galaxy. It beats slowly, but with unending power. Every flare, every burst, every newborn star is a reminder that even in the shadow of a black hole, life cosmic, radiant and eternal finds a way to shine. For now, Sagittarius A star slumbers in silence, its appetite subdued and its energy output faint compared to the raging quasars that light up distant galaxies. But astronomers know that this stillness is not permanent. Beneath its calm exterior lies a force capable of transforming the Milky Way itself. The black hole's history hints at a more violent past, a time when it may have burned millions of times brighter than it does today, releasing enough energy to shape the structure of the entire galaxy. Every so often the sleeping giant stirs, offering glimpses of the power it still holds. These awakenings are brief but spectacular, a reminder that even a quiet black hole can roar when provoked. Sagittarius A*'s dormant state is not due to weakness but scarcity. It has little to feed on. Most of the gas and dust near it orbits safely beyond its reach. Yet when a dense cloud or star wanders too close, the black hole's gravity pulls it apart, feeding on the shredded material and igniting bursts of radiation across the spectrum from radio waves to X-rays. In 2019, astronomers recorded the brightest flare ever observed from Sagittarius A*, a sudden outburst that increased its infrared brightness over 100-fold in just a few hours. It was as if the black hole had blinked awake, then fallen back into rest. The cause remains uncertain. Perhaps a clump of gas or a small planet was torn apart, momentarily fueling the black hole before vanishing into its depths. Events like this are more than cosmic curiosities. They are windows into the behavior of gravity at its most extreme. Each flare reveals how matter behaves when it is stretched, heated, and accelerated to near-light speeds in the black hole's magnetic field. The energy released in these brief episodes dwarfs anything humanity could ever produce. To capture these moments, telescopes across the world and in orbit watch Sagittarius A* continuously, waiting for the next flicker. NASA's Chandra X-ray Observatory, the Very Large Telescope in Chile, and the Keck Observatory in Hawaii all contribute to this cosmic surveillance. Together, they piece together the black hole's pulse, a rhythm of quiet punctuated by sudden violence. But these small flares are only whispers of what the black hole is capable of. Evidence suggests that several million years ago, Sagittarius A* experienced a true awakening. The discovery of the Fermi bubble's two colossal structures, extending 50,000 light-years above and below the galactic plane, revealed that a massive eruption had once erupted from the Milky Way's center. That explosion released energy equivalent to 100,000 supernovae, driving jets of plasma far into intergalactic space. For centuries, the shockwaves from that event reshaped the galaxy's structure, sweeping away gas and altering the course of star formation. The remnants of that ancient fury still glow faintly today, like smoke rising from a long-cooled fire. What triggered that outburst remains uncertain. Some theorize that a massive star wandered too close and was completely consumed, releasing a surge of radiation before vanishing forever. Others suggest that a large cloud of gas collapsed into the black hole, providing enough fuel to ignite a brief but spectacular quasar phase. Whatever the cause, it shows that Sagittarius A* is far from dormant in the long run. It is a creature of cycles quiet for millions of years, then active for thousands. These awakenings may be the heartbeat of the Milky Way, brief but transformative pulses that shape the galaxy's evolution. Even now, astronomers detect faint echoes of that power. Streams of hot gas and magnetic filaments near the galactic center appear to be remnants of smaller eruptions, miniature versions of the great event that formed the Fermi bubbles. The black hole may still be venting energy in subtle, periodic bursts, low growls from a slumbering beast. Understanding these cycles is crucial to understanding how galaxies live and die. When black holes feed, they release radiation that can either stimulate or suppress star formation. Too much energy, and gas clouds are blown apart, halting the birth of new stars. Too little, and gravity causes runaway collapse, forming too many stars too quickly. Sagittarius A*'s intermittent activity seems to maintain a balance, regulating the Milky Way's growth like a cosmic thermostat. Its quiet now may simply be a pause between heartbeats, a resting phase before the next flare. When it does awaken again, perhaps thousands or millions of years from now, the event will reshape the galaxy once more. Jets of radiation will pierce the darkness, lighting the core with brilliance unseen in human history. From Earth, the night sky will glow faintly from the galactic center, a distant fire rekindled after an age of silence. The sleeping giant will have stirred, reminding the universe that even in stillness, power endures. And when it settles once again into calm, the galaxy will bear its mark, sculpted, scorched, and renewed by the brief breath of its creator. Long before humanity existed, Sagittarius A* had already shaped the destiny of our galaxy. The faint glow of the Fermi bubbles and the trails of ionized gas still visible around the galactic core are relics of those ancient eruptions, echoes of a time when the Milky Way's heart burned bright. Millions of years ago, our black hole was not the quiet presence we see today. It was a raging quasar, consuming matter and spewing energy across tens of thousands of light years. The radiation from that era may have altered the chemistry of vast clouds of interstellar gas, triggering or halting the formation of stars far from the galactic center. The remnants of that activity linger like scars written across the Milky Way's body, faint but enduring signatures of an age of cosmic fire. To trace these echoes, astronomers look for evidence in multiple wavelengths: radio, infrared, X-ray and gamma ray. The picture that emerges is astonishing. High above and below the galactic plane, enormous lobes of plasma stretch like twin balloons, glowing faintly in gamma rays. These are the Fermi bubbles, discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope. They span nearly half the visible sky, each extending 50,000 light-years from the galactic center. Their edges are sharp, suggesting they were inflated by a sudden, massive injection of energy, something that could only have come from Sagittarius A star. The scale of that outburst defies comprehension. For a brief cosmic moment, the Milky Way's black hole must have shone as brightly as the entire galaxy combined, unleashing winds that tore through interstellar space. The shock waves from that event would have swept up surrounding gas, compressing it into dense shells that later became birthplaces for new stars. In this way, even destruction gave rise to creation. The galaxy's architecture, its rhythm of birth and death, was forever altered by that ancient eruption. But the Fermi bubbles are not the only witnesses to this history. Closer to the galactic center, astronomers have found filaments of hot gas glowing in X-rays, twisted by magnetic fields into long, narrow strands. These filaments act like fossils of magnetic turbulence, frozen remnants of the black hole's powerful jets. Some appear to be as old as 6 million years, roughly the same age as a massive burst of star formation observed near the core. It seems likely that both events, the black hole's awakening and the starburst, were connected. As Sagittarius A star erupted, it may have compressed nearby clouds of gas, igniting a wave of stellar birth. The evidence is written in the stars themselves. The youngest clusters near the galactic center, like the arches and quintuplet clusters, all date back to that same period. They are the children of the black hole's fury, born from the chaos it unleashed. Even the orbits of stars in the innermost region still bear the signature of those ancient forces. Some move in coherent disks, as though they were once part of a single massive gas structure spun into rotation by the black hole's feeding frenzy. Others race around at high speeds, perhaps remnants of disrupted systems flung by gravitational slingshots during that violent time. Every star near the core carries a story, a fossilized trace of a moment when the galaxy's heart roared to life. The echoes extend even to Earth. While the radiation from those outbursts would have been too faint to harm life here, traces of the event can still be detected in cosmic ray distributions and gamma-ray backgrounds. Our planet, orbiting quietly in the spiral arms, has been shaped indirectly by the forces that emanated from the center. The elements that built Earth: carbon, oxygen, iron, were forged in stars whose formation may have been influenced by the black hole's ancient activity. In a sense, we are distant products of Sagittarius A star's breath. Particles of its long-forgotten outbursts scattered through time and recombined into living matter. These echoes of the past remind us that black holes are not only destroyers, they are also cosmic engines of renewal. Their violence seeds the universe with structure, driving cycles of collapse and rebirth that define galactic evolution. Even now, as Sagittarius A star slumbers, the memory of its power persists in the geometry of the Milky Way, the symmetry of the Fermi bubbles, the distribution of stars, the flow of interstellar gas. It is as if the galaxy itself remembers, holding the imprint of its creator within its every motion. Someday, another awakening may come. The process will begin quietly, invisible to human eyes, as gas and dust accumulate once more near the event horizon. Then, suddenly, the past will repeat itself. Radiation bursting outward, magnetic fields twisting into colossal spirals, the galaxy trembling under the renewed voice of its central power. The echoes of the past will become the music of the present, and long after that moment fades, new civilizations perhaps far beyond our time will look upon the evidence and know that their galaxy too once burned with the fire of rebirth. Every discovery about Sagittarius A star brings us closer to the limits of what we can understand. The black hole is both a wellspring of knowledge and a mirror reflecting our ignorance. It challenges every law we thought was absolute, bending not only space-time but also the boundaries of human comprehension. For all our equations, telescopes and theories, the singularity at the heart of Sagittarius A star remains an enigma and object where gravity crushes matter, time and even information itself into a point of infinite density. It is not merely a gap in understanding, it is the frontier where physics as we know it collapses. Einstein's general relativity describes the black hole's exterior perfectly, predicting the warping of light, the bending of orbits, and the stretching of time. But step across the event horizon, and those same equations fail. Inside lies a realm that cannot be described by any existing theory. Matter is compressed to scales so small and energies so high that quantum mechanics and relativity, our two greatest pillars of science, cease to cooperate. This conflict between the very large and the very small is the greatest mystery in modern physics, and black holes are the battleground on which it will be resolved. Sagittarius A star offers us a natural laboratory for testing those limits. Every flicker of radiation, every motion of a nearby star, every ripple of gravitational energy carries clues about how space-time behaves at its breaking point. When we study the light near the event horizon, we are not just looking at a cosmic phenomenon, we are observing the seams of reality itself. The goal of future science is to understand what truly happens beyond that boundary. Does matter vanish into a singularity, or does it transition into something new, something beyond our current imagination? Some theories suggest that information is not destroyed, but encoded in the event horizon itself, forming what is called the holographic principle, the idea that our three-dimensional universe may, in some sense, be a projection of information stored on a distant surface. Others propose that black holes could be portals to other regions of space-time, connected through hypothetical wormholes. While such ideas remain speculative, they arise from serious attempts to reconcile quantum mechanics with gravity. Sagittarius A star in its quiet state gives us the perfect stage on which to test them. Its relatively small size and proximity make it a prime candidate for experiments that measure space-time distortions with unprecedented precision. Over the next decades, missions such as the Next Generation Event Horizon Telescope, space-based gravitational wave detectors, and infrared interferometers will refine our view of the black hole's environment down to scales never before imagined. We will see not just its shadow, but the dance of plasma and magnetic fields at the edge of the event horizon, revealing whether Einstein's equations hold perfectly or begin to crack. Already, hints of new physics emerge in the details. Some observations of flares near Sagittarius A star suggest that light behaves in subtly unexpected ways, possibly due to quantum effects at the smaller scales. These might be the first glimpses of the bridge between relativity and quantum theory, a path toward the long-sought theory of everything. Yet even as technology advances, one truth becomes clear. Black holes are not just scientific puzzles, they are philosophical ones. They force us to confront questions that cut to the core of existence. What happens to time when space ends? Can information truly disappear, or does the universe preserve every bit of reality, hidden somewhere beyond our reach? And if the laws of physics themselves break down at the singularity, what lies beyond the edge of those laws? In that sense, Sagittarius A star is both a cosmic object and a metaphor for human curiosity. It represents the horizon of knowledge, the place where understanding stops, but imagination begins. Every new observation pushes that horizon back a little further, revealing new questions, new contradictions, new wonders. The black hole challenges us not only to look deeper into the cosmos, but to question the foundations of thought itself. Perhaps that is its greatest gift. For while we may never see beyond its veil, the pursuit of that impossible sight drives science forward. The singularity is the universe's way of reminding us that mystery is eternal, and that knowledge is not a destination but an infinite journey. When we gaze toward the center of our galaxy, we are not just looking into space, we are looking into the very edge of reality, the frontier where the known dissolves into the unknowable. Sagittarius A star stands there, silent and patient, waiting for us to ask the next question. Though Sagittarius A star sits 26,000 light-years away, its presence is deeply connected to our existence. It may seem remote, buried at the galaxy's center, yet its gravity shapes the Milky Way we call home, influencing the very space in which Earth was born. Every atom, every star, every orbit we know exists within a galactic structure that this invisible giant helped design. But beyond physics, beyond geometry, there is something profoundly human in our relationship with the black hole, a thread of curiosity that binds our fragile lives to the vast machinery of the cosmos. For centuries, humanity has stared into the night sky, seeking meaning in the patterns of stars. We mapped constellations, told stories about gods and heroes, and gave names to the wandering lights. Yet even as we built myths, we sensed something deeper, an awareness of the unknown, of the silent void between the stars. Sagittarius A star embodies that unknown. It is a symbol of everything we cannot touch but long to understand. Its darkness represents the ultimate question mark of existence, the place where knowledge stops and mystery begins, and still we reach for it. The image of the black hole's shadow, captured by the Event Horizon Telescope, became an icon of human achievement not because it was beautiful in the traditional sense, but because it proved that even the most impossible goals can yield to patience, cooperation, and imagination. Thousands of scientists across continents worked together for years, linking observatories across the globe to turn Earth itself into one vast instrument. They spoke different languages, came from different cultures, yet were united by a single idea: to see the unseen. That image was not just a triumph of science, it was a triumph of humanity. It reminded us that in a world often divided by borders and conflict, curiosity remains universal. The black hole does not care who looks at it, what nation they come from, or what language they speak. Its truth belongs to everyone. To study Sagittarius A star is to recognize our own smallness and our shared capacity for wonder. In its shadow, we find humility. In its light, we find hope. The photons that circled the black hole before reaching our telescopes travelled for 26,000 years, beginning their journey long before civilization existed. They crossed eons to deliver their message, that the universe is far larger, older, and more interconnected than our fleeting lives could ever encompass. When we look at that faint, glowing ring, we are seeing both the past and the present, a collision of time and meaning. It is a reminder that while we are transient, the act of seeking knowledge grants us a kind of immortality. Every discovery becomes a bridge between what we are and what we could become. Sagittarius A star is also a mirror, reflecting our desire to understand ourselves. The black hole consumes everything that falls into it, yet from that destruction emerges clarity. We learn that endings are not voids, but transformations. Just as a black hole's gravity warps light and time, our questions about it bend the trajectory of our own understanding. It challenges our species to think beyond comfort, beyond survival, beyond the narrow horizon of everyday life. It asks us to imagine the universe as it truly is, vast, indifferent, and yet filled with meaning because we choose to seek it. There is something poetic in the idea that the same physical laws governing the fall of an apple also describe the motion of stars around a supermassive black hole. That unity of scale, the bridge between the intimate and the infinite, is what science ultimately reveals. It tells us that we belong to the cosmos not as observers but as participants. The iron in our blood was forged in ancient stars that once orbited near black holes like Sagittarius A star. The atoms that make up our bodies are literal stardust recycled through generations of cosmic death and rebirth. To study the black hole, then, is to trace our own ancestry, written not in words, but in the language of gravity and light. And in that realization lies the deepest connection of all, that the universe is not a distant stage but a living system of which we are a part. We are the eyes of the cosmos, the way it looks back at itself and asks, why? Sagittarius A star, in its silent pull, reminds us that our search for knowledge is itself a form of creation. It's how the universe learns about its own nature through us. Every question we ask, every measurement we take, every theory we test is an act of cosmic self-awareness. The black hole may never speak, but in our attempts to understand it, we give it a voice made of data, imagination, and wonder. And through that voice, the universe whispers back, "You were never separate from me." At the center of the Milky Way, where light seems to vanish, there exists not emptiness but an endless exchange of energy, gravity, and meaning. Sagittarius A star stands as the perfect paradox of existence, the darkest place in our galaxy, and yet the one that illuminates our understanding most. It is both the end of all things and the beginning of something greater. Around its shadow spins the fiery ring of matter and time, glowing with the final breath of stars that once shone across the galaxy. Those photons, trapped in orbit for ages before escaping, are messages from the edge of reality. They remind us that even in the deepest darkness, light finds a way to endure. The black hole does not destroy light. It bends it, shapes it, and reveals its resilience. In that transformation lies a profound truth about the universe and about ourselves. We too live in cycles of collapse and renewal, drawn by gravity toward the unknown, reshaped by forces we cannot always see. Sagittarius A star is not a cosmic monster. It is a reminder that endings are never truly final. The matter it consumes is not lost but reborn, its energy recycled into the fabric of creation. In that sense, the black hole is the universe's engine of continuity, a furnace that transforms chaos into order and silence into possibility. From the ashes of falling stars come new generations of suns, planets, and perhaps even life. The energy radiated from the galactic center flows outward, touching everything in subtle ways. The atoms that form our bodies were once part of these cycles, scattered across time and space, drawn together again into consciousness that now looks back and asks, "What am I made of?" The answer, whispered by the black hole's glow, is simple. You're made of the same fire that circles the event horizon. You are the universe, observing itself through borrowed eyes. That awareness, the ability to wonder, is the light that never fades. When we look into the image of Sagittarius A star, we are not just seeing a celestial object. We are witnessing a moment of contact between human curiosity and the infinite. The black hole's ring is the mirror of our own persistence, proof that even faced with the impossible, we reach farther. It took generations of scientists, thousands of minds across continents, to piece together that faint, grainy image of the galactic core. The light that travelled 26,000 years through the void met detectors on mountaintops and in deserts, synchronized by atomic clocks, united into a single vision. In that act, we demonstrated what the cosmos itself teaches us, that everything, no matter how distant, is connected. Every equation written, every telescope turned skyward, every dream of understanding forms part of a chain that stretches from the first spark of curiosity to the last photon escaping the edge of time. That chain is unbroken. Sagittarius A star may one day exhaust its surroundings, fading into a perfect black sphere, silent and still. But even then, its story will continue, written in the motion of stars, in the structure of the Milky Way, in the elements that compose life itself. The energy it once released will echo across billions of years, diffused into the cosmic background. The light may dim, but the memory of that brilliance, the pattern it left behind, will endure. Perhaps that is the ultimate lesson of the black hole, that immortality lies not in permanence, but in influence. Nothing lasts forever, yet everything leaves an imprint, a resonance that shapes what comes after. The same is true for us. We are finite beings bound by time, but what we create, our ideas, our discoveries, our wonder, extends beyond our brief lifespans. The act of understanding itself becomes a form of light, an energy that outlives its source. To contemplate a black hole, then, is to meditate on the eternal balance between disappearance and legacy, silence and echo. In that balance, there is beauty. The universe is not indifferent, it is participatory. It allows us to see, to think, to question, to dream. Every question we ask is a spark against the dark. Every revelation, a photon that escapes the pull of ignorance. Sagittarius A star, for all its gravity, cannot trap the light of human curiosity. It draws us closer, but instead of consuming us, it expands us. It forces us to grow in mind and spirit. That is why, when we gaze toward the galactic center, we are not simply observing the abyss, we are witnessing our own reflection, magnified across cosmic time. In the end, perhaps the most profound truth is this: there is no contradiction between eternal night and endless light. They define each other, one gives meaning to the other, and within that eternal interplay, the universe continues to evolve, to learn, and to shine. The black hole remains silent, but its silence speaks the language of gravity, of time, of awe. And through us its story will be told again and again, as long as there is light left in the universe to carry it forward.